Hi everyone, and welcome to today's lesson. This one is our first video using PD. That is our derivation system in the language of PL. So it is much like ST+, except there are 4 quantifier rules, which we're going to cover today. So these are the problems that I'll be showcasing. Now they are not that complicated. And I will be assuming that you are comfortable with ST+. There will be one more video with slightly more complicated problems later on, but this will get us going for the moment. Okay, so first it asks us to construct a derivation from that set to that sentence. So, well, we know the setup for this. It is quite simple. You take the content of the set and you set it up at the top of the derivation as your assumption, and then you go ahead and draw the sentence to be derived as a conclusion at the very bottom of your scope line. So that is what I've done here, and it looks like a simple just changing of quantifiers. You go from universal quantifier x to universal quantifier y. So it looks pretty simple. All you have to do is take off the quantifier, the x, and then put on another one, the y. So this is simple enough. Here's how it's done. In step 2, you go ahead and remove that universal quantifier. So that's line 1, universal elimination. And what we've done is we've just given it the individual constant a. Now think about this for a second. If all x are fx, that means that a has this property f. So if every single thing, that's what the universal means, has this property f, that means a has this property f. So this is a perfectly valid move. There is a way to translate it into natural language that makes it easy to understand, but I think just the rules alone should you should just focus on that. You don't think about English too much. At least when you're working on these. Okay, so line 2 is perfectly legal, and if that is the case, then we can actually use line 2 to get to line 3. So what's going on here is simple universal introduction. All you have to do is check that that individual constant you're moving from, it isn't in the target sentence, and it's not. I don't see a anywhere in line 3. Lowercase a, and you also have to make sure it's not in the assumptions, in the premises. Again, I don't see a lowercase a anywhere in the premises. So line 3 is a legal move. That's how universal introduction works. Okay. Next problem. Again, we have a set, 2 sentences this time, and a sentence to be derived. I've set that up at the bottom there, and the content of the set I've put into the assumptions. So there they are. It looks like the sentence to be derived, existential quantifier fx and gx, that just is 2 sentences with their individual constant replaced with a variable. So it looks like it's just first a conjunction and then an existentially quantified sentence, right? So we have to go kind of in layers here. So the first thing we want to do, let me rephrase that. The main operator of the sentence to be derived is an existential quantifier, but in there we also see a conjunction. So we have to go in that order. We have to get the conjunction first, what's further inside first, and then what is the main operator goes last. So the first thing we have to do is combine these sentences. That's a simple ampersand introduction. And notice that once we have done this, now we can existentially quantify this sentence. So that's line 3, existential introduction. All we've done is, instead of saying Bob is F and Bob is G, right? Lowercase b will stand for Bob. You're just saying someone is F and someone is G. And that's okay. That in natural language, that makes perfect sense. The rule also allows us to do that. And we've also followed all the rules. We've gone from the logical operators that are further embedded in the sentence to the ones that are outside. So we went from conjunction into a extensionally quantified sentence. So the analogy that I like to give sometimes is, obviously you put on your socks before you put on your shoes. So whatever's inside has to go first, and then whatever's outside goes last. So in this case, the ampersand is inside, the existential quantifier is on the outside, so that goes last. That's kind of the analogy that I think you should run with. Okay, moving on. Here is another setup for another derivation. It looks like we have to go from a universally quantified sentence to an existentially quantified sentence. So premise one, all it's saying is that for every x, some property h applies to y. And the sentence that we're trying to derive, we're just trying to say there is an x such that property h applies to y. So it's a simple swap of quantifiers. So we can definitely do that, especially because we're moving from universal quantifier to existential quantifier. Of course, if it applies to everything, which is what universal means, it applies to some things, which is what existential means. So let's begin by taking off the universal quantifiers, and then we'll put on the existential quantifiers. But as I said earlier, just like you have to put your socks on before you can put your shoes on, you have to take your shoes off before you can take your socks off. So the same thing goes here. If you're trying to eliminate quantifiers from a sentence, you have to go from the outside to the inside. So for this one, we're going to go ahead and eliminate the outside universal quantifier first for all x, and we're going to replace that x with an a. Of course, it applies to everything, so it applies to a certainly. So line 2 just simply is taking the outside quantifier from line 1 and replacing the variable that was associated with it with an a. In line 3, I'm taking out that second quantifier for all y. So now we have a simple predicate letter with two individual constants just like that. So 2 steps of universal elimination. So now A has some relation H to B. Well, we can begin to introduce existential quantifiers. So again, now we have to put our socks on and then our shoes. So we have to do the inside one first. If you look at the bottom sentence, the sentence to be derived, it begins, the most embedded component of it is the existential y. So we have to put that one on first. So the y corresponds to the second lowercase letter. So this line replaces b with y and puts the existential quantifier to the left. And then we can finally put on the outside quantifier, the main operator, and we replace that a with an x. So that's how this process goes. Take off your shoes before you take off your socks, and put on your socks before you put on your shoes. That's sort of the order that you want to keep in mind whenever there's two quantifiers, which is the most I'll ever give you. Okay, let's continue here. This one now is going to show you maybe the toughest rule that we're working with, also maybe the most counterintuitive, but certainly the most powerful. Existential elimination is a weird rule, but it is also weirdly powerful. So here we have an existentially quantified conjunction, as you can tell in premise 1. And we want to go at the bottom there to a truth functionally compound sentence. At the bottom, it's just a conjunction. So it's almost like we took off the existential quantifier, we separated the conjunction, and then we put on separate existential quantifiers for each of them and then put them back together. So if that's what it looks like we're going to do, that's a good bet as to how we should continue here. So what we're going to do is we're going to go ahead and assume we're going to use existential elimination. Now, the rule for existential elimination is you make an assumption from premise 1 or from whatever existentially quantified sentence you want to eliminate the existential quantifier from. So you begin with the assumption 2, right? FA and GA. And you just have to make sure that the individual constant that you are using, which in this case is a, doesn't appear in any of the assumptions. So I don't see it up there anywhere in line 1. It also can't appear in the sentence that you're using for your exponential elimination. In our case, that's actually premise 1. So it's not there. We've already checked. So it isn't in the assumptions. It isn't in the sentence we are taking the extension quantifier off of, which is number 1 again. And it also can't be in the target sentence. Our target sentence is at the bottom there, second to last line. And I don't see a, lowercase a, anywhere in there. So again, we just have to make sure it's not on those 3 places. And as long as we are sure about that, we are allowed to make this assumption. So line 2 is legal. Let's go ahead and see if we can break these up and add exponential quantifiers to each of them separately and then put them back together. So of course, that is perfectly legal. That's just an ampersand elimination from line 2. And now that we have FA, the easy existential rule is existential introduction, and that looks pretty straightforward. If Albert has some property F, then someone has this property F. So we just replace A with lowercase y and put an existential quantifier on it. Line 4 is perfectly legal. Let's do the same now for GA. So we take it out of line 2 with ampersand elimination, and we once again put in a variable in the place of the individual constant. And of course, line 4 and line 6, we selected the variables that we needed. Obviously, we didn't just slap on any variable on that existential quantifier. We put in the y with the f and the w with the g, because that's the sentence we're trying to derive. So we're thinking ahead there. In line 7, all we did was combine line 4 and line 6 with ampersand introduction, and that is our target sentence. So if you have reached your target sentence in a subderivation for existential elimination, you are allowed to end that subderivation and go ahead and justify your last line of that subderivation on your main scope. And you have to cite it this way. You have to cite both the line that you used so there's a subderivation itself, lines 2 through 7. But remember that assumption for that subderivation, it came from line 1. Just look at it. Line 1 is an existential quantifier fx and gx, and all we did for line 2 is take off that existential quantifier, that's why it's called existential elimination, and replace those variables with an individual constant, a in this case. So for line 8, our justification is 1, which is where we started with, and 2 through 7, that entire subderivation that assumed an existential elimination of 1. So that is how you justify those. I know these are hard to kind of wrap your mind around in natural language. Some people look at this rule and they say that doesn't make any sense. I guarantee you that if you work through a problem in natural language, all of this is actually perfectly legal. I mean, it even makes it is logic after all, it makes perfect sense actually. But when we remove the natural language and just look at the syntactic relationships, some of the meaning is obviously lost. But you must trust these rules. And I recommend you do all of the homework assignment and maybe do it again, just to make sure you really harness or you really kind of master these new quantifier rules. And then we'll work on some tougher problems next time. Any questions? Shoot me an email. I will talk to you soon.